All right, good morning, everybody. How are you today? It is Monday, April 13th, 2020, that really windy day outside. And I'm here to go over the review I sent you to do. The review is 10 questions long and is everything I need you to be able to do to solve separable differential equations, or just differential equations in general. So I'm going to go over it with you, see if you have any questions. I will be available online tomorrow during our third block normal time. If you have any questions, any further questions, or if you want me to explain this in a different way, just come on, hop into the session and ask me any questions you want. But I thought I would give you this so you could look over this and rewatch it if you want to, and maybe it'll help you out. There is a typo. I hope you got that on the note. It's on number 2, and I'll show you that when we get there. But the first 3 questions were verifying that functions are solutions to differential equations. So remember, differential equation is an equation that's written with derivatives involved. So this is x times y double prime equals y prime. I'm asking if this equation here is a solution to that. Well, I know what y equals. I know that y equals x squared plus 3. Its first derivative is 2x. And its second derivative is 2. So I'm going to plug all that in here and see what happens. So x, y double prime is 2. Y prime is 2x. So I think it's pretty obvious that 2x equals 2x. So yes, I have just verified that that is a solution to that differential equation. All right. The typo was with number 2. It was a PDF document that I had already downloaded, and I wasn't able to change it, so I wrote you a note. It should be this. It's 1/4 y double prime minus y equals 0. Is that a solution to this equation? Well, here's our equation. I need to find the second derivative. So the first derivative, remember that's the first. The first derivative is, remember the function of e is its own derivative, e to the 2x, times the derivative of the exponent. Derivative of 2x is 2. So this function has a derivative of 2e to the 2x. We continue along, and its second derivative, well, 2 is a constant, that will stay. E to the 2x, the derivative is e to the 2x, times the exponent again, which is 2. Then it'll be 4e to the 2x. And I could take this derivative forever. The third derivative would be 8e to the 2x. The fourth derivative, and so on and so on and so on. But here's what I got. I only need 2. So 1/4 of the second derivative, which is 4e to the 2x, minus y, and y was e to the 2x, equals 0. So e to the 2x minus e to the 2x, well, that equals 0, and I know that 0 equals 0, so that's a verification. All right. Seem okay? Well, let's move on. One more. X natural log of x. Is that a solution to this differential equation? By the question, I'm asking you to verify, so it is true. You might get questions that ask you, is it true? Not to verify, so you have to make sure it works. So now we have x natural log of x. That's our function. All right, its derivative. Now it's going to be a product rule. So it's going to be the first times the derivative of natural log plus, now we reverse it, the derivative of x times the second. Do a little simplification. We see that x times 1 over x is 1. So our derivative is 1 plus natural log of x. So let's plug it in here and see what happens. So 1 plus the natural log of x minus 1 over x. And our y value is x ln of x. Now, depending on how good your algebra is, you can tell right away if this is going to work out. So, or if you're like me, or if you're like somebody who says you got to verify it, you got to show me more work. So when I multiply this through, these x's will cancel. natural log of x minus natural log of x is 0. It leaves 1 on this side, 1 on that side. Verify that it's true. And that's how you verify a solution to a differential equation. Now, how do you find a solution to a differential equation? Now remember, change that y prime. Multiply both sides by dx, because we have to separate them. I won't say the song, I promise. All right, all the y's on this side, all the x's on this side, so now we can integrate. Remember, separate, integrate, and solve. The antiderivative of dy is y. The antiderivative of this, let's see, it's 3x cubed over 3, so it's x cubed. The antiderivative of 1 is x. And again, there's this plus c because we're not sure if it has a constant value. So if I take the derivative of this, I get 3x squared plus 1. Derivative of constant is 0. That's what you do. That's it. Let's try to separate and solve this one. Okay, so I'm going to multiply e to the 2i times this side. I'm going to multiply dx over here. This is what I end up with. Separated successfully. Now we integrate. So remember, the derivative of e to the 2i and the antiderivative of e to 2i are the same. However, be careful. Remember, we're taking the antiderivative, so it's like reverse of everything. So the chain rule says that this derivative should be 2. Well, if it's a derivative, we always multiply by the 2. But since it's an integral, we're dividing by the 2. And just think about it in reverse. If I took the derivative of this, the derivative of this would be 1/2 e to the 2y times 2. That 2 and that 1/2 would cancel out. The antiderivative of 3x squared is x cubed plus a constant. Now we got a little bit more work to do because we got to solve it for y. So I'm going to multiply everything by 1/2. E to the 2y equals, oops, forgot the 2 already. 2x cubed plus 2c1. Remember, I put the c sub 1 because I know I'm going to change that constant around a bit. And now to solve for an e, to eliminate an e, remember its inverse is the natural log. So that means that 2y equals the natural log of 2x cubed plus 2c sub 1. I'm going to divide it by 2. And we can just call that thing just a giant C now. And that's one way to do it. That would be fine. That is one solution to that differential equation. As long as you solve for y, that's fine. Now you can manipulate these logs and rewrite them differently and stuff like that. You could. But in this case, that's fine. All right. How about this one? X squared plus 1. We'll change that to dy dx. xy. So I got to pull the y over to this side. And now I'm going to divide x squared plus 1. And also multiply dx. Dx is over here. The y's and y's over here. We're separated. Integration time. The antiderivative of 1 over y is natural log of y. That's a nice one. This one, a little bit more work to do. Okay. So we use a u substitution method that u equals the denominator x squared plus 1 its derivative is 2x. Again, a couple ways to do this one, but I figured the easier one is that I need a 2x dx. I've got the x, I've got the dx. I don't have a 2. I can build in a 2, but I have to counteract that 2. So I'm going to take a half to the outside. So 2 times a half is 1. That counteracts it. So remember, all of this here, this 2x dx, that all becomes du. And this x squared plus 1 becomes u. So let me rewrite this now. This is going to be 1/2 the integral of, this is all du, and this is u, 1 over u du. What's the antiderivative of 1 over u? Yes, it is the natural log of u. We'll give it a little constant there. And that equals this. All right, not done. Obviously, we didn't solve for y, and we need this in terms of x, not in terms of u. So u equaled x squared plus 1. We're going to put that x squared plus 1 back. And there we've got it so far. So now, a couple ways to do this problem. I know we got to, the inverse of those is e, so we take them all to the e. This 1/2's a little weird though. So I don't know, I might do this. Yeah, I think I will. Remember your log rules. If you have a constant out in front, that becomes an exponent. So this all goes to the 1/2 power, and the 1/2 power is a square root. Now the reason I did that was because it makes this next step easier. So if I do the e, the inverse, so this is y, this is e to all of this. Well, what is e to the natural log of, well, this just becomes x squared plus 1 times e to the c sub 1. And that e to the c sub 1 is just some constant. There's an answer right there for you. Now what I have not included in this review is initial values that solve it for C. I can give you a couple of those problems if you'd like to try them. I probably will, just to make sure. Because I'm going to post a test on this on Wednesday. So I just realized I was going over this, I forgot a problem like that. I'm sorry, but we'll put one on there. All right, next part is growth and decay. So here you go. What do we got here? Let's highlight some key features of this problem right here. Bacteria increases constantly at a rate proportional to the number present. Once you see that, you know this is true. We learned that from a differential equation. Now we have some values here. There were 400. Very good. So now that tells us our C value. Our C is 400. What else are we given? We are given that the number triples in 6 hours. All right, so our T is hours. So we have a data point here. We know the number triples. So we know the 400 becomes 1200 in 6 hours. Now if it triples, you know that if we divide, to solve this, divide both sides by 400, we get 3. there's our triple value right there. E to the 6k. And solve for k, so natural log of 3 equals 6k. So let's shoot it up here. Our k value would be the natural log of 3 over 6, which is about, and I didn't do this in advance, so excuse me. So the natural log of 3 divided by 6 is approximately 0.18310. So our function is going to be 400e to the 0.18310t. Now the question we must solve, how long will it take to reach 1 million? So I want to know, when is this going to be 1 million? You can solve it any way you want. If you want to put on your calculator and solve it, you want to solve it with logarithms. Remember, on the AP test this year, you'll have full use of your calculator, but the questions won't be like this. You won't have to use your calculator to solve it. Now, doesn't mean the questions will be easy in sense of numerically, but you won't have to worry about any of the larger crazy numbers. So let's just solve this one. I'm going to divide by 400. So what's a million divided by 400? Should probably know that one. Yeah, I probably should have known that one. But you know me, and numerical calculations is not my strongest point. All right, natural log of both sides. There we go. So to find my t value, I'm just going to take the natural log of 2500 and divide it by that number right there and see what I get. So natural log of 2500 divided by 0.18310 is, we'll just go 2 decimals here. Just 1 is fine. So it will only take less than 2 days, 42.7 hours, to get to 1 million bacteria. It's growing pretty fast. All right, 42.7 hours. Okay. 3 more to go. Now this is a Half-Life problem. So, not that you could tell that I made up that radioactive element. That's not really real. That's my last name, and that's the year I was born, and that's my date of birth. It's all on here. Sorry. Sometimes I don't get very original with my numbers. But here we go. It decays at a rate proportional to the amount present. So once you know that, here we go. CE to the KT. 30 grams were present initially. So there's my 30e to the KT. All right, because that's my 30. Now, it has a half-life of 712 years. So which means in 712 years, I'll be 15 left. Or, since you know it's a half-life, when I divide both sides by 30, I get a half. There's my half-life. Whoops, forgot my E. All right, so to solve that K value, natural log both sides, the natural log of a half. Natural log of E is an inverse. So my K value will be the natural log of a half divided by 712. Well, what do we got? Natural log of 0.5 divided by 712. Nice small number. Let's see, we got 1, 2, 3, 4, 7. we want our k value is negative, and that's important because we're decreasing. So that's why the k value is negative. So our equation becomes 30 e to the negative 0.000973 That's our equation. Our question was, how many grams will be left after 1,000 years? So now we're simply plugging in 1,000 for our time. Now I will be using this decimal approximation. If you use a calculator, you can use significantly more digits. So if you use your calculator, you might get a different answer if you don't round the way I did, but that's all right. The process is the same. I get, it's supposed to be 1,000. I get 11.3. Now that should be in years. Oh, no, I'm sorry. That's 1,000 years later. That's how many grams we have. Kind of makes sense, I hope, in the sense of the question, because the half-life is 712 years. Well, it went from 30 to 15 and 712. 12 years after that, it should be down then to 7.5. So that falls inside that range, so that seems like a very reasonable answer. So 11.3 grams are left. All right. Slope fields. I want to ask you to do your own slope field here. I got 15 points. Not the most fun, especially when we got something like this, but let's see if we can find any patterns. So this defines our slopes. Y prime equals x squared minus y. So what we'd really do is we just pick data points and we plug in numbers. Because what do I have to do? There's three things I want. I'm going to find my y prime value by putting in x's and y's. So what's the first point you want to put in? You want to start right smack dab in the middle? At the point 0, 0, what's the slope? Well, what's 0 squared minus 0? All right, it's 0. So what happens when we go up the y-axis? What about the point 0, 1? Well, we get 0 squared minus 1, so a slope of negative 1. What if we go to 0, 2? We get 0 squared minus 2. This is getting steeper as it goes up. So maybe it might follow that as it goes down, it switches. Let's find out. 0, negative 1. Sure enough, it's going to be 0 minus negative 1 or 1. Which would lead you to believe that this should be 2. Because it would be 0 minus negative 2. All right, that's what we have there. And we'll put it this way just so that we know. Okay, let's do these. We have negative 1. Negative 1. Whoops, we'll go 2. We'll go to the one point up here. Negative 1, 2. So we square x. Negative 1 squared is 1. 1 minus 2 is negative 1. So this has a slope of negative 1. And we'll go down. So negative 1, 1. Let's see what we got. Negative 1 squared is 1. 1 minus 1 is 0. So here we have a slope of 0. All right. At the point negative 1, 0, we will have negative 1 squared, which is 1. Remember, these slopes don't have to be perfect. Just kind of get the right idea. Right, at the point negative 1, let's see, negative 1 squared is 1. 1 minus negative 1 is 2, so it's a little steeper. And it might follow then that this is even steeper still. Negative 1 squared is 1. 1 minus negative 2 is 3. So yes, even steeper. It doesn't look steeper, does it? So these are not always fun, easy to draw. It's supposed to be a little steeper than that. Okay, again, I'm not looking for perfection, and neither would they look for perfection on AP test, just a general idea. All right, and we have one more. Let's see if I can duplicate this one, bring this one over. All right, now we have our last set of points where we've got 1. So we got the point, and we'll start up here at 1, 2. All right, 1 squared is 1. 1 minus 2 is negative 1. Oh, so that's interesting. At 1, 1, we have 1 squared is 1. 1 minus 1 is 0. Looks like it might be the exact same as this one, because we're squaring it, so it doesn't matter if it's negative or positive. We're squaring at x. Let's see, 1 squared is 1. 1 minus 0 is 1. I think we can say that these will be the same at 1, negative 1. Let's see, 1 squared is 1. 1 minus negative 1 is 2. So a little steeper than the 1. And 1, 2. Again, 1 squared is 1. 1 minus, oops, sorry, that's negative 2. 1 squared is 1. 1 minus negative 2 is 3. So this is a little bit steeper. Okay, so this is a general idea of what it looks like, and it's pretty good. It's pretty good, but that's how you do a slope field. And lastly, all I'm asking you to do here is what would, using this direction field, what would these look like? So you can kind of see that the numbers are here. Y of 0 is 1 is right here. All right, I'll put that one in blue. So the question is, where would this go? So it just kind of follows the field. And it goes like that. Okay. What if we started at 0, 0? Well, kind of pushes it down, then pushes it up. Kind of the same thing over here. Kind of pushes it over and pushes it down. And lastly, what if we started here at 0, negative 1? So it kind of flattens out first and goes up fast, and then kind of comes down like that. So that's how you would draw a direction field based upon an initial value. So I hope this little review helped out. I'm going to send you a little bit more, to some extra things that I forgot to put on this one. But if you have this, you got the basic idea, and you should be doing okay. So feel free to drop into third block class tomorrow if you'd like to ask any questions. And I hope you have a great day. Bye.